In Math 1, we studied linear functions and exponential functions almost exclusively. This year in Math 2, we've looked at a new function for us, quadratic functions. Not that we didn't know about them in Math 1, but we've studied them a lot this year. And one of the things we've had to do is solve quadratic equations. So this is a quadratic equation. I recognize that it's a quadratic because it does have a quadratic term, right? It's got x to the second power. It also has a linear term, negative 2x, and it also has a constant, negative 15. This is asking us to solve this quadratic by using the factoring technique. In general, what we do is this quadratic right now is written in what we call expanded form, and in order to solve it, we're going to convert it into the factored form. And then once it's in the factored form, we use the zero product property. So realize that when something is factored, it's in the form like, x plus a times x plus b if there's only two factors. And if this is something that equals 0, the zero product property assures us that the only way that that's possible to get a product of 0, if you multiply two things and get an answer of 0, is if one of these things is actually 0. So the zero product property allows us to take each one of the individual factors, set them equal to 0, and then solve for x. So that's what we're going to do here. So we begin by factoring this quadratic. And this is a pretty straightforward quadratic to factor. And in fact, I think I could just write the x, and I'm looking for factors of negative 15 that have a sum of negative 2. And I immediately think of the 3 and the 5, and I need a negative 2, so I would make it a negative 5 and a plus 2, and that equals 0. So if I verify this, x times x is x squared, and then I've got a 2x and a minus 5x, whoops, which would be negative 3x. Uh-oh. Oh, I'm sorry, this is supposed to be a 3. Thank you. Uh, Negative 5x plus 3x is indeed 2x, and then finally negative 5 times 3 is negative 15. Now, I can do that because I've been doing this a lot, and really, if a quadratic is factorable, and you notice that the leading coefficient is the number 1, probably you should be able to do that too. Now, alternatively, one of the tools that we have is considering a generic area model and a diamond problem. So for this problem, if I looked at the generic area model, I would have an x squared down here, a negative 15 here. The product of those two is negative 15 x squared. And because I need this generic area model, I need the area of this to represent x squared minus 2x minus 15. So I need to have a negative 2x in it, and you can see it doesn't right now. So I need the other two boxes to have a sum, this box and this box, to have a sum of negative 2x. Now, how I break that up is guided by this diamond problem. And with negative 15 as my negative 15x squared as the value that I'm starting with, I know that the factors of that I can play with are 1, a 3, and a 5. And I quickly settle on the fact that I'm going to have a negative 5x and a positive 3x. So if I write those here, negative 5x and a positive 3x, and again, it doesn't matter where I write those and which boxes I write those, I can quickly pull out the greatest common factor. The greatest common factor this direction is simply an x. The greatest common factor this direction is also simply an x. The greatest common factor this way, I'm going to go ahead and bring out negative 5. And the greatest common factor this way, both of those are divisible by 3, so I'm going to bring out the positive 3. So you can see I'm left with what? The product of x and minus 5 and x and a positive 3 is equal to the generic area model there. So this factors as x plus 3 times the quantity of x minus 5, which is what I got up above. So now that this is factored and I demonstrated kind of the simple way that you can probably start doing with more practice, and the way that we've done it often, the generic area model and the diamond problem, is because this is equal to 0, right? I can now use the zero product property and set each one of these equal to 0. For this case, x would be -3, and for the other one, I've got x minus 5 equals 0. Therefore, x is the number 5. So my two solutions here are -3 and +5. And if I were to plug either one of those numbers in for x squared, I would see that I do indeed get 0. And just to do one of them, it's nice to check. If I plug in -3, this would become a 9. -3 times -3 is indeed 9. And then I would have -2 times -3 would be +6. And 9 and 6 is 15. And then when I take away this 15, right, I do indeed get 0. So 9 plus 6 minus 15 is 0. So I verified that one of the two answers works. So let's go ahead and do this something similar with the second example here. This one I'm going to go ahead and use the generic area model and the diamond problem right off the bat, although it's not necessary. I have 2x squared and a -5. This is -10x squared. And I need to get a sum of 3x. And the two values that do that, 10 doesn't have a lot of factors, right? It's a 1, a 2, and a 5. The two that I'm going to use are, and I can see because this is negative, one of these must be negative and one must be positive. And coupling that with the fact that this is positive, the sum is positive, I know that the positive one has to be larger than the negative value. So I am looking at here a positive 5x and then a minus 2x. And this is exactly what I need. That product is the product of 2x and positive 5. I'm sorry, the product of -2x and positive 5x is -10x squared, and their sum is 3x. So in here I'm going to write the -2x and the 5x, and then I'm just going to go ahead and factor out the greatest common factor. The greatest common factor this way is going to be 2x, and then I'll take out this greatest common factor. The greatest common factor for those is just going to be just plain old x. Now that I've factored out the 2x, I can see this one, there is only the factor of -1, which is nice because it does agree with the fact that 2x times -1 is supposed to be -2x. And then finally, this one is going to have to be a positive 5. So this is the unique factorization. That's the thing that's amazing, right? If we eliminate the common factors first, this is the only way that we can factor this polynomial. So let's go ahead and write this now in factored form. Whoops, the factored form would be, this is equivalent to x minus 1 times the quantity of 2x plus 5, and this equals 0. So now we just use our zero product property and we write x minus 1 is 0, therefore x is the number 1. That's one of our solutions. And 2x plus 5 is 0, therefore 2x is equivalent to -5, and x is equal to -5 halves. So this is our second solution. In question 32, this is kind of setting the stage for solving quadratics, perhaps by completing the square. It says find the value that completes the square for each of these. Let me look at a small graphic for this one. So if I'm looking at x squared plus 8x, how do I complete that square and what does it look like? So if I go all the way back to Math 1 or perhaps your 8th grade math course and look at some algebra tiles, this is x squared and then plus 8x. So how do we build a perfect square out of this? Well, I can line these up, right? These x tiles here. I'm trying to make a perfect square. And it becomes pretty evident that I'm not going to just bring all of these along here. So to make a square, what we do is we take half of our x tiles, right, and we put them along here. And as I do this, right, I can see that, yeah, this is going to allow us to make a square. You can see our dimensions across the top are x squared plus 4. These are each 4 long, and x squared plus 4. The question is, what do I need in here in order to complete the square? So if I snap an image of that so that I can write on this, again, what is this? This is x, and then this is a 1, 1, 1, and 1. So that's the x plus 4. And the other one is an x and then a 1, 1, 1, 1. So this is also x plus 4. And the number of unit tiles that are needed to complete the square is 4 times 4, or 16. So as long as our leading coefficient in our polynomial is 1, and remember what we started with, we had x squared plus 8x, and we're asked what do we put here to complete this square. As long as the coefficient of your squared term is 1, the shortcut that we've settled on is, well, we're simply taking half of these. Why? Because half of them will go along here and half will go along here. So that'll make it a nice square for us. And then the number of tiles that we need to complete that square is just half of this, and then raised to the second power, right? 4 times 4 is 16. So that's how we complete the square. What's nice about this is once you complete the square, right, it is easy to take the square root because this is a perfect square. So it's a technique for solving a quadratic because you can take the square root of an expression that has a perfect square or on each side of an equal sign and eliminate the squared term. So using all that, we're just going to go ahead and say that to complete this square, we're going to take half of the negative, not negative 12, half of negative 20, and we're going to square that. That ends up being negative 10, and negative 10 to the second power is 100. Over here to square this, again, we're taking half of our 8, and when we square that, half of 8 is 4. 4 squared is 16. So that makes these both perfect square trinomials. For 33, we're asked to solve a quadratic by using the quadratic equation. This is part of the, I would say, the quadratic formula. It is a quadratic equation, and the quadratic formula does have two parts. It essentially says if you have a quadratic in the form ax squared plus bx plus c, in other words, a is the coefficient of your squared term, b is the coefficient of your linear term, and c is the coefficient of your constant. It's not a coefficient, it's just your constant. Then you can find the roots of that equation by considering this expression, right? The opposite of b plus or minus the square root of b squared minus 4ac, all divided by twice a. So for this particular problem, right, I can see that I have an a value that equals 3. I can see that b is negative 3, and I can see that c is negative 5. So now that I know I've identified what a, b, and c are, I'm just going to plug them into this formula. So the first thing I see is the opposite of b. So I notice that b is negative 3, so instead of writing negative 3, I'm going to go ahead and write 3. And then I have plus or minus. This is how we get the two different roots, potentially, as long as there are actual roots. Then I'm going to go ahead and look at the part inside. When I take b and square it, that's a negative 3 times a negative 3. So I'm looking at the square root of 9 minus the number 4 times the number a, which is 3, times the value of c, which is negative 5. So I have inside of the parentheses something, and down below I'm going to write 2 times 3. I'll just go ahead and write that as 6. That's 2a. Okay, so if I simplify this a bit, in fact, I just want to particularly focus on the root part. This is going to be 9 plus, let's see, 4 times 3 is negative 12, and I believe negative 12 times 5 is 60. So what I've got here is a positive 60, right, because I've got a negative 4 and I'm multiplying that by a negative 5. So this is 60. So inside of here I have the square root of 69, which is not a perfect square.
So this definitely will not have, this would not be factorable, but we can still get it solutions even though it's not factorable. So root 69. And let's see, I guess the answer then that I would look for, it would be 3 plus or minus the square root of 69 divided by 6. Now, one of the challenges is this is not a standard way of writing this answer. And if you're presented with a multiple choice test, you may want to look at decimal equivalents of this expression. So if you had those, then you could compare them with decimal equivalents of your answer choices and see which ones were equivalent. It turns out this number 69 is divisible by 9. No, it's not. 69 is divisible by 3. Oh, actually, that's not something we can simplify. So that would be our answer. So there are two answers here, just so you understand what they are. One of them is 3 plus the square root of 69 and then divided by 6. And the other answer is 3 minus the square root of 69 divided by 6. And if your answer choices were decimals rounded to the nearest tenths, you would want to evaluate those expressions and use those answers. So the next thing we have are a couple of things involving imaginary numbers or complex numbers. And the one main idea we keep coming back to is what happens when you take this imaginary index I and you square it, you get the number -1. Turns out neither one of these are going to involve I squared because we're just adding and subtracting these complex numbers. So in the first one here, you can see there's nothing to distribute except for +1, so it doesn't change the things inside of the parentheses at all. Same thing here, right? It doesn't change them. So this is equivalent to 7 minus 4i plus 10 plus 2i. So if I simplify that, I'm looking at 17, and that would have to then be a minus 2i. And that's the answer. Pretty straightforward, really. This one is, let's see, this would be a -10 and a minus 2i, because I'm going to distribute this -1 to both of these things inside. That would give me a -3, right? What is that? That's 7 minus 4i minus 10 minus 2i. So the -3 is -10 plus 7. And then I have -4i minus 2i, which would be -6i. So that's our answer to this problem. And actually, there is one example here where we're going to see our I squared. So I'm going to multiply these. It's a binomial, right? There's two different things. They're complex numbers times another complex number. Um, One of the things you could use is you could organize this with a generic area model, just to see the 4 different parts you get when you multiply a binomial times a binomial. So I've got 7 and then -4i, and I've got 10 and +2i. This is the number 70. This is -40i. This is +14i, and this is -8i squared, right? I times I is I squared. Before we simplify our answer completely and finish up, let's consider what this is, right? It is not -8 I and then that quantity squared. It's just a -8 and then I itself is squared. And remember, when we square I, we get -1. It's the only, that's the weird thing about, interesting thing, I guess I should say, is that normally when you multiply something by itself, you always get a positive result. In this case, when you multiply I times I, you get +1. I'm sorry, you get -1, which is unusual, right? Normally you get a positive value, but here I times I is -1. So this is equivalent to -8 times -1, which is equal to just +8. So if you look at it, this is not an I at all, right? This is just the number 8. So my simplified answer, I can combine these two because they are like terms, right? I end up getting 78I. And if I combine negative 40 and positive 14, I would get negative 26i. I'm sorry, why did I write an I? There's no I there. It's 78 and then plus, um, I'm sorry, and it's 78 and then minus 26i. I guess I'll try to be a little bit more precise here in what I'm saying. But let's look at this again. 70, and then this is a plus 8. This is positive 8. 70 plus 8 is 78, and negative 40i plus 14i is negative 26i. So this is the simplified form of this. I've multiplied this out, and I dealt with the fact that I had an I squared, which equals negative 1. And then the final thing that's on this page are our special right triangles. And probably we should take a moment and just kind of talk about special right triangles in general. There's two that we looked at, or there are two that we consider. One of them is a 45, 45, 90. And the thing about this is it's clearly an isosceles triangle, so we've got congruent base angles. So here's our thinking. If this is x, right, this clearly must also be x. And with those both being x, right, we can use the Pythagorean theorem to figure out what the hypotenuse is. And we did this a couple times in class, but let's just say that this is, I'm just going to call this something ridiculous. I'll call it smiley face for just a moment. And let's figure out what that is. So we know that x squared plus x squared is smiley face squared. So what we have here is 2x squared, right? There's two of those, is smiley face squared. And if I take the square root of both sides, what do I get? I get the square root of 2x squared. And that's what smiley is. And I'm just considering the positive or principal root because this is the length of a side of a triangle, so the negative root doesn't make sense here. So I can simplify this further, right? Because this is a perfect square and these are factors. It's 2 times x squared. I can write this as x times the square root of 2. And that's the thing that's in our notes, right? If you have a 45, 45, 90, each of the legs, if each of the legs are x, the hypotenuse must be x times the square root of 2. So what's nice about this is if you're told, let's say that this is a 3, you know that this side, right, you just multiply by root 2 to get how long this side is. This side would have to be 3 times the square root of 2. Right, so again, if you have a 3 here, this side is 3 root 2. And you know, this is a simple example too, but if you're told that this is 10 times the square root of 2, right, in order to go from here, from this side, whoops, I didn't mean to do that. In order to go from this side to the other side, what we do is we are going to divide by root 2. So as I'm moving from the hypotenuse to this side, I'm dividing by root 2, and I get that this has to be simply 10, and the other side is 10 as well. The spot where it's a little bit more disconcerting, I guess, or a little bit more difficult, or some of us struggled with a little bit, is let's say that I tell you that this is just the number 5. Okay, if this is 5, how in the world do I figure out what the other side is, the side labeled x? Well, again, as I move from the hypotenuse to the leg, what I do is I divide by root 2. So as I'm moving this way, I'm dividing by the square root of 2. So this could be written as 5 divided by the square root of 2. But and you know what? If you leave your answer there, that's fine with me, particularly in this course. If you're presented with a multiple choice answer and you don't see that as a choice, you might compare the decimal equivalents to other choices. But the other thing that we talked about is how do you rationalize that denominator? How do you make it so that it doesn't have a radical in it? And in order to do that, you could multiply both the numerator and denominator times the square root of 2. The thinking here is that as I multiply by root 2 over root 2, I'm multiplying just by the number 1, so I'm not changing the value of this, I'm just changing how it looks. And when I do that, in my denominator, I have root 2 times root 2, which simply equals 2. in my numerator, I'm end up with 5 times the square root of 2. So interesting fact, this 5 times root 2 divided by 2 has the exact same decimal equivalent answer as 5 divided by root 2. And really, it's for historical reasons in mathematics that we prefer this answer. There really isn't a modern reason that this answer is superior to the one that's highlighted in purple, um, but it's kind of a legacy idea that some people just can't let go of. The other special right triangle that we looked at was the 30, 60, 90, and if we consider just the big picture of where this comes from and what it was, right? We started by thinking about an equilateral triangle, and if it's equilateral, we know that all the sides are x long, and actually for convenience, I'm going to say all the sides are 2x long. It doesn't matter what I call them, but just because I want a certain result, I'm saying they're 2x long. If we were to bisect this segment, right, and drop an altitude here, we end up getting a right triangle. These sides are both congruent, and they share this side. So these two triangles are congruent by side, angle, side, right? We've got this side that they share, the right angle, and this side that they share, right angle, and this side. So they're both congruent by side, angle, side. And this side down here ends up being half as long as the original side, so it's just x. Well, if it was an equilateral triangle, all these angles had to be 60, right? And if they're congruent triangles, this has to be a 30-degree angle. So that's the genesis of our 30, 60, 90. We don't write that diagram like that. We just like to know where this came from. That's a terrible looking triangle. So this is where it comes from. Here we've got our 60-degree angle, our 30-degree angle, and our 90-degree angle. And what we're saying is if this is 2x and this is x, this side over here is something. And I know a lot of you are saying, yeah, it's x times the square root of 3. Where does that come from? Well, same thing. It's the Pythagorean theorem. If I consider this to be quote-unquote side length smiley, I have smiley squared plus x squared equals, and then this 2x gets squared. When I square twice x, 2x times 2x, I get 4x squared. On the other side, I have smiley squared plus x squared. And if I take away an x squared from each side, I get smiley squared equals 3x squared. And the principal root of that, right, is this. It's 3, the square root of 3x squared. And you can see I can simplify this. X squared is a perfect square, so I can bring it out. So it's x times the square root of 3. This is what you have in your notes. This is what you've dealt with. This is the square root of 3. So again, in a 30, 60, 90, this is probably the thing you want to make sure you have in your notes. For a 45, 45, 90, this thing is what you want to make sure you have in your notes. Probably a cleaner version would be nice. 45, 45, 90. We've got, here's our 45, 45, 90, and we just had x, x, and x times the square root of 2. So make sure those are on these pages, and then you kind of understand how to use them. Let's go ahead and look at the 4 problems that we have here real quickly, and we'll apply these. So in this first one, you can see this is kind of the worst case scenario. This is the part that we were calling x times the square root of 2. These sides are each x, but I need to figure out what that is. In order to move from this 12 to this side, I'm going to divide both sides by the square root of 2. So I'm taking 12 and I'm dividing by root 2. And I'm going to simplify this by multiplying this by, again, by a root 2 over root 2. This gets rid of the radical in my denominator. I'm left with, in my numerator, 12 times the square root of 2 over 2. And you can see 12 divided by 2 is 6. So the preferred answer form for this, again, for historical reasons, would be 6 times the square root of 2. And you can see that would be both b, and because it is isosceles, right, it would also be a. So they're both 6 times the square root of 2. For the next one, this is easy, right? This is clearly 17, and this is clearly 17 times the square root of 2. So I hope if you see a question like that, you're quickly able to get this solution. On this one, this is a 30, 60, 90. Remember, the one across from the right angle is the one that we were calling 2x. The one across from the 30-degree angle we're calling x. And the one across from the 60-degree angle we were calling x times the square root of 3. So if 54 is 2x, I know that half of that's 25 and 2 more is 27, right? Uh, 54 divided by 2 is 27. And once I have that, then the other side, right, has to be the square, that times the square root of 3. So this should be 27 times the square root of 3. So my sides are E would be 27, and the other side I have there, this F would have to be 27 times the square root of 3. Let's move along. This is probably one of the worst case scenario ones, right? Here's the 60. And across from the 90, we call this 2x. Across from this, we call it x. Across from the 30 is x. And across from the 60 is our x times the square root of 3. So our x times the square root of 3 is 27. If I want to know what this side is, I have to divide by root 3. So this is going to be 27 divided by the square root of 3. And that's a fine answer. However, if it's multiple choice and you don't see that, you have to rationalize this denominator or compare decimals. I'm going to multiply by root 3 over root 3. And when I do that, I ended up getting a 27 times the square root of 3 in the numerator over 3. And it turns out 27 divided by 3 is 9. So my value for x, right, this side, would be 9 times the square root of 3. What is that? That's 27 divided by 3 times the root 3. And if that's what g is, if I double that, I get this side. This side is going to be 18 times the square root of 3. So those are our three sides for that, right? One of them was 27, g was 9 root 3, and h is 18 root 3. And then our final one here, again, this is a pretty nice one. You can see this is the side that we call x times the square root of 3. And just by looking at this, I can tell that x has to be 10. This is the side that we call x, and x we just said is 10. And then if I double that, I get the hypotenuse. This hypotenuse has to be 20. So here, k is 20. Whoops. And I would have to be 10. And that's it for this page.